right, so welcome. This is the last talk of the last day, so this is clearly the hardcore crowd here. I hope I can keep you awake through the duration of the talk. So I'm here to talk about SQL-H, which is a product that Aster has announced at Summit. And our intent here is to give you a way to run SQL analysis on your data that's stored in Hadoop, and that has so far been locked away from all attempts to analyze it using SQL and using BI tools in a natural way. So the outline of the talk is, I don't want to assume that everybody here knows about H catalog. I don't know how many of you sat at Alan's talk on H catalog. So I'll do a quick primer of H catalog. I also don't want to assume everyone knows about Aster, so I'll do a quick primer on Aster, and then talk about SQL-H, the definition and the feature set that it provides, and then go through a bunch of examples. This is meant to be a technical deep dive. There'll be a lot of detail here, and I hope at the end of this, you guys leave with a detailed understanding of how SQL-H works, what the integration points are, and what to expect when you use this in production. All right. So H catalog, for people who don't know what H catalog is, H catalog provides a way in which you can do table management and storage management for HDFS data. So, you know, you put data in HDFS, but it's extremely difficult to standardize across your organization what data is in there, what format it's in, and how you can get to it. So H catalog is an Apache project which ships as part of HTTP 1.0, and that presumably in the future will be in other distributions as well. And it provides a shared schema and data type mechanism for your data in HDFS. I highly recommend it. It's a really great project. It provides this table abstraction so that users don't have to worry about where their data is and how it's stored, the format it's stored in. And over time, as you modify the contents of your data in HDFS and as you change the way you want to interpret it, it lets you adjust to that. It also gives you I think it's undersold, it also gives you a very good polymorphic view on your data. So you can take your HDFS data that's stored in one location and get different views on it, right? Where you can look at it in a different way depending on the kind of analysis you're doing on it. And it provides interop across data processing tools such as Pig, Hive, MapReduce, streaming, everything. It's meant to be a generic data access mechanism. It uses Hive-like DDL commands in order to actually create your views on the data. And we look at a few examples there. It supports tables, views, partitions, just like Hive does. It provides parallel load and store interfaces. So it's not just a way of defining where your data is, but it's also a way of, it also gives you methods to access that data in a parallel way across your nodes. And it's agnostic to the actual file format of the stored data. Everything is, you can plug into H catalog any sort of file format you want to. You just have to write the appropriate converters. It currently supports these file types in its first release, and it'll support everything else coming forward. So here's some example syntax in H catalog, in Apache H catalog, of how you create a relational view of your data that's stored in Hadoop. At the bottom of this create external table statement, you'll see a location, HDFS://data/Apache log. So this is pointing to a particular directory in HDFS. And the rest of the statement is expressing how you convert the data that is stored in files in these directories into relational tuples, right? So there's a SERD, there's a serialization, deserialization Java class associated with the table. Data in that HDFS directory is passed through this SERD in order to read and to write to that data. The SERD has particular properties. So in this case, it's a regex SERD. And then the properties indicate what sort of formats, what pattern to look at in the regex to get the tuple out. This is not a complete syntax. The input.regex is actually a lot longer, but it didn't seem relevant to this talk. And then, of course, the view coming out is this relational view. You get these tuples, with this nice named table and these named columns, so that it looks a whole lot like a SQL table, or it looks exactly like a SQL table, and you can actually access this in a declarative way in other languages and be able to access this data. And hopefully the benefits of this are obvious. You do this, this sort of view creation once. You use it across all your Hadoop usages. And I just want to clarify something because there's been confusion about this. This is entirely like an H catalog interface to create a table, right? This has nothing to do with Aster at this point. This is how you present your unstructured data in a structured manner to other users. And so here's an example, like going down into the details a little bit. This is how you read data from H catalog. The job controller of the job that you're running, and this could be a MapReduce job, it could be a Hive or a Pig job. The job controller will pass in the table name and the partitions that are of interest to the H catalog server. The H catalog server hands you back a list of objects which are essentially splits of this data. Then the job controller will distribute these splits out across your Hadoop system so that there's a single split that goes into each map task. And then the map task will use the split to access the data. And the data comes in from wherever the source is and gets converted into these tuples that are then passed on to this map task. And as you can see, the design is very, it's very well thought out and very elegant and simple. Your source data can be anywhere. It can be in HDFS. It can be in S3 if you're running on the cloud. The create table can deal with that, and the input splits can deal with that. And the task of interpreting, of figuring out how to read this data and how to convert it into a standard format, that task is delegated to the input splits in H catalog, right? And irrespective of whether you use this in Pig, Hive, just straight MapReduce, streaming, whatever, it's the same mechanism, and it works uniformly across them. You just have to write, one more layer on top of the split in order to fit into these various subsystems. So moving on, I want to do a quick primer on what an Aster data system looks like. So Aster data is an MPP SQL database. It's fully ACID compliant. We have multiple tiers of nodes. We have the queen tier and the worker tier. This is what the queen node looks like. The queen node is on your left-hand side. Users will connect into the queen node and communicate via SQL and SQL MapReduce. The queen node has a SQL engine consisting of a parser, a cost-based optimizer that's able to optimize both SQL and SQL MapReduce, and then an execution engine that knows how to take this query and be able to run it in parallel across all of the nodes. The worker tier consists of worker nodes. On the right-hand side of your screen, there are 2 worker nodes. So each worker node hosts a set of data partitions. I want to talk a little bit about partitioning because we have 2 ways in which we partition data. Initially, data is hash partitioned into a particular data partition, and then within each data partition, you're able to logically partition your data based on ranges, based on lists, based on inequality, things like that, equality, inequality, things like that, so that you're able to further sub-partition the data within each data partition. And the SQL optimizer is able to take advantage of all of this stuff so that when a query comes in, it knows exactly what to do so that the least amount of work is done on the system and it's as efficient as it needs to be. We have a module that we call the Intercluster Express, which is able to move tuples across nodes if necessary across the worker nodes in order to execute this SQL or the SQL MapReduce program. Regarding SQL MapReduce, Aster has been doing SQL MapReduce for a long time. Aster was inspired by Google's paper, just like the Hadoop community was. And for a long time, Aster has had a facility in which you can write snippets of code in Java and have it run in the MapReduce framework, in the MapReduce paradigms, and have it run on the cluster. And Aster took it one step further in the sense that they've always, from the beginning, been able to run this along with your SQL, so that you look at a system as a normal relational engine. You have a bunch of tables. You can work with them in SQL, join them together, filter, do predicates, all of this stuff. And then whenever you need to step out of SQL, because the kind of analysis you're doing is not optimal for SQL, you can step out of SQL, run some MapReduce code in order to transform the data in some particular way, and then go back into SQL and do further joins with the other data, maybe jump back out into maps and reduces. So Aster's been always able to pipeline your processing between your SQL and MapReduce steps. And the other thing that Aster does really well is SQL optimization. We have a cost-based optimizer. We have a lot of information about your data, like demographic information. And with MapReduce tasks, there's always been a sort of conflict with SQL optimizers that you don't know a lot about the output of a MapReduce task. You've taken all these tuples, you've passed it into this bit of code, and this code is like throwing out this information, right? And you don't have enough information about what that code did in order to optimize the later pipelines well. So Aster's always done progressive optimization, where we look at the data that's coming out of the MapReduce tasks, and we are able to collect demographic information on that data so that we can plan out the future execution steps really well. I'm saying all this in some detail because it's all relevant to the later slides, and when we get to that, I'll point that out as well. Okay, so with those two primers out of the way, let's get to SQL-H itself. So SQL-H essentially provides you with direct access to H catalog data within AsterDB. So H catalog tables are available without duplicating any DDL commands on the Aster side, which means from the Aster system, you can say, I want to grab table web logs from this H catalog server, and Aster will query the H catalog server via its REST API to figure out what that means and be able to access that data. H catalog tables are, they're first-class objects within AsterDB, which means anything you can do with a regular SQL table in Aster, you can do with the H catalog table. Because of things like progressive optimization, we are able to do this particularly well, which means we'll actually optimize the SQL paths for H catalog tables once they're in our system. And we use the H catalog interfaces that I showed you before to read tuples in parallel on all the data nodes. So to go through that in some detail, I have slides very similar to the slides I showed you earlier with the H catalog read flow, but this time they apply to Aster, right? So this is how Aster reads from an H catalog table. During the query planning phase, the Aster optimizer will send in the table name and partition information to the H catalog server node. And we'll talk some more about the partitioning information because there's something special the query optimizer does there that we'll talk about as well. The H catalog server, does what it always does, which is it returns back a list of splits that are necessary in order to read this information. And then in this figure, we're looking at, I've blown up a single Aster worker node. There are multiple data partitions on this worker node, and each data partition has its associated ARC engine. I'm sorry, I should clarify. ARC stands for Aster Relational Compute, and it's our relational execution engine that does the SQL and SQL MapReduce execution. And then each ARC engine has a few splits associated with it, and it uses these splits in order to read information directly from HDFS, right? So from the previous figure, we are getting information, we are getting metadata information directly from the H catalog server, and once we do that, we are reading in actual data directly from HDFS. We actually have a tunable knob here in terms of how many splits are read in parallel by each ARC engine. There are multiple use cases for tuning this both up and down. You may want to tune this up if you have an extremely large Hadoop cluster and a smaller Aster cluster. You may want to tune it down if it's the other way around. And you may also want to tune it down if you want to reduce the amount of load that the Aster SQL execution places on your Hadoop system. But anyway, in the end, you have an ARC engine that's able to pull in a set of tuples directly from HDFS and convert it into tuples. And once it's tuples, this is bread and butter for Aster. Once it's a tuple, we can deal with it really well. We have all the right paradigms for that. Okay, so now I want to talk a little bit about what this enables, because I think this feature is, on its face, it's a very straightforward and simple feature, but if you look at what it enables and what it gets you, I think it's very powerful. So So the interactions of the Aster system are simply with the HCatalog master server and HDFS. So that means we do not use up any MapReduce slots on your Hadoop cluster, right? You still have all the MapReduce slots that you had earlier in order to do work on Hadoop. And the Hadoop system can be used for other activities simultaneously. Aster runs native HCatalog input reader code for translating HCatalog table names into input splits. So what that means is that there is absolutely no mismatch between these two systems, and anything that works with HCatalog is expected to work with Aster, right? Post qualification and all that stuff. But it's designed to be a very simple integration so that going forward we don't have any maintenance issues. It should just work as is. And everything supported by HCatalog interfaces is supported in Aster. So that includes, for example, partition pruning, which we'll talk about in some detail. And in the future, as there's more support for filtering support and other kinds of pushdown in HCatalog, then we look to use that as well. And any changes, so when you looked at the execution flow, you noticed that Aster was talking to the HCatalog server to get metadata information directly from there, which means any changes that were made on the HCatalog side are reflected immediately on the Aster side, right? We're not caching anything, we're not tracking the information, so any new tables that are created are immediately available, modified schemas, new partitions, everything is immediately available. There's no multi-step DDL that needs to be done. In terms of usability, I think this is very important. What this gives you is you now have full integration with BI tools, right? So you can use Tableau, MicroStrategy, Business Objects. You can use any of these tools that you're used to using to work with SQL. And this works with data that is residing in Hadoop, right? And that it works entirely transparently from the tool's perspective. They just talk to the Aster system. This also means that you can use data in Hadoop along with data that's sitting in your Aster system. And because obviously Aster also has an extremely good connectivity layer with Terdata, right? So if you have a Terdata EDW in your organization, you have a Aster system for an analytics platform, and you have a Hadoop system in which you have a bunch of archival data, you can now use Aster to access all of this information together. And we are working very hard at Aster to make sure that all this works really well and seamlessly and in a very performant way. So previously using data from multiple systems, is more complicated. You have to move data over, worry about whether it's stale, things like that. So. And obviously, it's full SQL support. HCatalog table data can be inserted into a SQL flow, just like any native Aster table. There's absolutely no differentiation on that. And if desired, of course, this provides a load pipeline into Aster from Hadoop. So if you're using your Hadoop system in order to do some ETL, you can do that on the Hadoop system. And then if you want to actually load it in a permanent way into Aster, you can do that as well. It's very straightforward. We look at some example usage later, but it's as straightforward as you would expect, essentially. Okay, the other thing that's really important is that Aster has spent a lot of time building a set of analytical foundation tools. So we are very proud of this. We have a very large suite of tools that are available out of the box. We do time series analysis, path analysis, statistical, relational, all this stuff. And we've been doing this for a long time because Aster has always seen itself as a big data platform to be used by data scientists and by quants to do a lot of analysis. And so we do a lot of these functions really well, and we're very proud of them. Aster's MapReduce framework is also polymorphic and provides for a lot of flexibility in the use of these tools. So you can use them against any tables. You can pass in various parameters to tune their behavior. It's always been built for this sort of usage. So now all of this functionality that we built in Aster and tried to productize and perfect over time is now available against your Hadoop data. And we think this is actually very, very powerful and very, very important. It's also, of course, available against your Hadoop data, joined with your Aster data, joined with the Terdata, and all of that stuff, right, which makes it more interesting. So we think this makes users productive faster, or we think this will make users productive faster. And you spend time actually analyzing data, not building functionality and tools. You don't spend time, writing code in Java, worrying about data formats, et cetera. You're actually looking at your data and trying to understand it, which is what we wanted. And a few notes on performance. So partition pruning is transparently supported. So our SQL optimizer is able to look at your query. So here's an example query. You're just selecting tuples from Hadoop web logs, which is clearly a table in Hadoop. that we access via H catalog, and you're saying where date stamp is some particular date stamp, right? So our optimizer is actually able to query H catalog and figure out that DS is a partitioning column, and then we're able to figure out that this is a valid partition, that the 2012 06 10 is a valid partition, and then we will only read in the data from HDFS that is in that directory, right? So our optimizer automatically deals with this for you, and there's nothing special you have to do in order to get this partitioning working. You just work naturally in a SQL world and let the SQL optimizer work for you. And I have a few notes on performance. I think this is very important because the first thing you think of when you think of a connector like this and moving data across is you think the performance is probably going to be worse than it would be if you didn't move the data across, right? But there's a few really important things here. I mean, data transfer is required, but the network may not be a bottleneck. It all depends on how your system is built out. Many Hadoop clusters today don't have very highly performing disk subsystems, and many Hadoop systems do have a well-connected network. So depending on the size of your system, the data transfer may not be a bottleneck because your network may not be a bottleneck. It may just be your disks that are a bottleneck, and in that case, you're bottlenecking on both systems. Additionally, depending on what you're doing with the data, the time taken for the initial data read, like the first read from disk, that may not be the largest amount of time on your system, right? Typically, the initial data read is pretty quick, but then you have a long workflow with multiple MapReduce jobs that have to do a lot of intermediate storage, intermediate representations, and multiple transformations, and that takes a whole lot longer than that first read. So the only thing this impacts, even if your network is slower than your disk, is the first disk read. And we believe that the rest of the steps are substantially faster. So Aster's native SQL execution engine has been built from the ground up to be really good at SQL, really good at optimization, really good at all of these things. And so it's at this point a whole lot faster than Hive's MR-based execution engine. And as queries get complex, this performance advantage just increases, right? Because Aster is able to do a lot of interesting things. And one of the things that's very important here is progressive optimization, because we look at like demographic information and your input double sets, we're able to do a lot better in terms of picking the right plan for the later stages of the query. And if required, you can reduce the impact of this on the Hadoop system, and you can like reduce the network bandwidth usage by passing in a few parameters that say how heavily you want to hit your Hadoop system with the data reads. And so here are some example SQL syntax. So this is remote catalog listing. So Aster has a client-side tool called ACT. These are like screenshots or I don't know, console dumps from that tool. So you can say extl to list out all the information on an H catalog server, and that shows you the list of databases. The second thing here is to look at the tables in a particular database. So here I've added in the database equals production line. And here we've added in one more parameter, which is the table equals table name, and you can look at the actual columns that are inside a table, right? And one of the columns that's listed here that's important is whether a particular column is a partitioning column or not. And you can see in this example that the DS or the date stamp column is a partitioning column, and this is what the optimizer uses to make the choice on when to move the partitioning query, partitioning pruning inside H catalog. So in order to access data from H catalog, there is a base MapReduce function called load from H catalog, to which you pass in the server name, the database name, the table name, and the columns that are of interest. And one of the things here is that if the columns that are of interest are smaller than all the columns in that table, and if your table is stored as an RC file table, then we will optimize how we read this data as well, so that we only read a subset of the actual tables, right? I mean, we don't actually do anything special for that. It's just the HCatalog input splitter is going to be able to read that data directly from HDFS, so that just works for us naturally. And then you can create a view on top of this table and on top of this MR function. And once you create a view, this is something that can be used in any place that a regular Aster table can be used, and you get all the functionality of the Aster table in there. So some of the later examples like this one will presume that a view has been created. So in this case, Hadoop_weblogs is a view on that HCatalog table. So here is an example syntax of data load from HCatalog into Hadoop. into Aster. As you can see, it's very straightforward. You just do a ctask, create table, Aster table. The distribute by hash is a hint to the Aster optimizer about how you want to store the information in Aster so that later queries will run faster. And then you just do a ctask and you just do a select star from the Hadoop table. It's as straightforward as you'd imagine. And here's an example of the partition pruning. In this case, I'm showing you the catalog for a table with DS as a partitioning column. And because DS is a partitioning column, the query at the bottom of your screen is actually going to just pull in information from a particular HDFS directory and not from all the directories for that table. And what I want to just emphasize here is the naturalness of just saying select star from table name where, and then everything just works. So here's I'm just showing a couple more slightly complicated queries. This one's an example of a join. So you can just join two tables together like you would expect. It just works. And here's a SQL MapReduce example. So in this example, what we are showing is invocation of npath, which is a MapReduce function that we have for path analysis. And so the first thing to notice is that this is happening on Hadoop web logs, which means it's happening on a table that's stored actually in Hadoop. The second thing is, npath itself is very flexible. It has you can create all these symbols on the fly. You can say what sort of symbol paths you're looking for, and you can group the information on the inside and the outside in the right way. And it's very flexible, so you can change what you're looking for. You may be looking for people who've gone to the home page and then to the checkout page and then somewhere else, and you can change all this stuff around by just changing what these symbols mean, right? So our MapReduce framework is full of functions like this that give you very flexible ways of looking at your data, both your structured and your unstructured data, and to be able to get information out of them. And now all of that is available on Hadoop data as well. And just because the console logs are not interesting, there's also screenshots from Tableau. So in this case, we are looking at path analysis on data that is partially stored in Aster and partially stored in Hadoop. So some of the information, so on the left-hand side, there's a set of events. So the user in this case is like a user of wireless provider services. And the event on the right-hand side is a cancellation event where he's canceled the service. And the points in the middle map all the points of contact that the user has had with the wireless provider, whether it's in store or online or somewhere else. And this is just showing you all the last few paths that a user goes through before he cancels the service. Right? So this is a little noisy, and there's ways of filtering this information out and looking at the most common paths that the user had before he canceled the service. And in this example, he's happened to visit the store as one of the last few steps before he cancels the service, and this tells you that there's probably something you can do in store to help him out or to prevent him from canceling the service. And so I think the example is not important. What's important here is that you can do this information now. You can do this sort of analysis now on data that's stored in Hadoop and in Aster, and also presumably in your data warehouse, because we have Terdata connectors that work really well as well. And you can do all of this in a visual way without someone going in and worrying about how to write code to get all this working together and how to move the data across these systems. And so we think this enables a lot of very interesting functionality, and I'm excited about seeing our customers using this and the ways in which they use this, and also the ways in which it falls apart and you have to figure out what's wrong and fix it. So, and that's all I had. If there's any questions.
One question here, you're talking about accessing the Hadoop data from the Aster. Is there any way, can the reverse also be done? Say, for example, the Terdata table be registered through the H catalog, and from the Hadoop side, say using Hive, we can see the data from the Terdata.
No, you cannot at this point. You cannot create a H catalog table that refers to data in Aster. That's what you're asking, right? It's kind of a natural step for us to look at in the future, but we haven't done that right now. Our focus has been on, how do we enable our users to use like a SQL front end to get all this stuff working together. But that's something that we'll be looking at as well.
Okay. Do you have any inclination like what kind of timeline you're going to do to get the reverse done?
No, sorry, I don't control timelines.
Okay, thank you.
Yeah, I was wondering if there's anything that ties this specifically to HCatalog, or if it's in fact possible to run it on top of the Hive Metastore.
To run out of the Hive Metastore, I think it's possible. So, I mean, we've been looking at, so HCatalog is of course like, it's come from the Hive Metastore, right? And there's just some minor changes around that. I see no reason for us to not be able to run on the Hive Metastore. If we have enough demand for that and if people ask for that, then we'll look at supporting it. There should be no reason not to do it.
Thanks.
All right, I think we're done. Thank you very much.